Okie dokie, chemists, let's get started. So the plan is today is to work through a little bit more of chapter 12. We're definitely not going to finish it, but we will get to parts of the chapter that will be covered in the LCP lab tomorrow, so Le Chatelier's principle. So we'll look at equilibrium constant from a qualitative standpoint. I will point out that I'm going to cancel office hours right after class because I want to yeet home to beat the storm. So if you have questions about something, just follow me to my office while I pack up. But I'm going to be leaving right after class. So make sure that if you have to be on the road today, follow safe driving distances between you and people around you. Want everyone to stay safe. Okay, so let's continue talking about chemical equilibrium, big K. Last chapter, chemical kinetics, was about small k, equilibrium constant. We're going to talk about big K, so equilibrium constant. This is the idea that at a certain point in time, reactions achieve chemical equilibrium, where the forward rate is equal to the reverse rate for an elementary reaction, and we can express the ratio of products to reactants present at equilibrium based upon just some numerical value. But the expression for equilibrium constant depends on what reaction is happening, what reaction is at equilibrium. So here we have a reaction between nitrogen, hydrogen, and ammonia, and so the Kc expression is always products over reactants, where the coefficients become exponents. So that's the general form of the Kc expression. Here Kc stands for concentration, so everything is in molarity. But here we can talk about Kp as well, where P stands for pressure, and this is important for gases. Gases can have a concentration or pressure, and that's where we left off last week. And that is comparing Kc and Kp for a sample. So, like I said, gases can have a pressure and they can have a concentration. Let's remind ourselves with Pivner, the ideal gas law. PV equals nRT. A gas sample can have a pressure. So if I rearrange some stuff, if I divide both sides by volume, you get that pressure is equal to N over V RT. So we see pressure is proportional to N over V because RT is a constant. RT is constant for a sample. What is N over V? N is number of moles. V is volume. So what is that unit called? Molarity, moles per volume. So we just proved here that pressure of your sample is actually proportional to the molarity of that gas sample as well, moles per liter. Okay, so to convert between Kc and Kp, what we could do is convert every single one of these concentrations to pressure and then plug it into the pressure equation, but that's not necessary. We can kind of combine it and use math logic and recognize that there's this factor of RT that relates pressure and its concentration, right? So here's pressure, there's concentration, RT just stays constant. So if we look at a reaction and just count, how does the number of moles change of gas for the sample change? We can relate Kp and Kc by a factor of RT to some exponent, where Kc times RT times the change in number of moles of that reaction, or to that exponent, is equal to that Kp for that reaction, so expressed in pressure terms. So to get delta N, so the change in number of moles of a gas sample, simply all you need to do is count the number of moles of gas on your product side. So here there are 2 moles of gas on the product side, but then how many moles of gas are on my reactant side? 4, perfect, so 4 moles. So delta N is always products minus reactants, or final minus initial. So here it's 2 minus 4. So delta N for this reaction is -2, meaning that in the course of the reaction, we're losing 2 moles of gas in this sample. So that delta N is important for us to convert between Kp and Kc at a certain temperature because they're related by a factor of delta N. And so let's actually calculate this. So at this temperature, The equilibrium constant for the Haber process is about 10. Let's calculate Kp at this temperature. So simply we are using this expression, Kp equals Kc RT delta N. So note we are using the gas law version of, the ideal gas law version of R, because we're converting pressures to molarity. So we're using the ideal gas law. So use that kind of R. We are given Kc, R is a constant, temperature is given to us, and delta N we just found out is -2. So the hardest part here is just getting that delta N. How is the moles of gas changing in the sample? It's typically count the number of moles of gas in your products minus reactants. That's what it is. So here's -2. So it's just plug and chug now. So 9.60 is Kc times a factor of RT, so R is 0.08206, times temperature, so 573 Kelvin, times, to the -2 exponent. So simply, this inside that parentheses is something like 47 to the -2. And so we get that Kp is equal to 9.60. If you take that to the -2, you get something like 4.5 times 10 to the -4. All right, so that is the RT factor that converts all of those concentrations to pressure. So it converts to pressure, and then you get some number in the corner there, all right? So we see that Kp, when these gases are expressed in pressure terms at their chemical equilibrium, the value is a little bit different. When it's in concentration, it's near 10, but when they're in pressures, a slightly smaller value, but they still represent the ratio of products over reactants at equilibrium. Okay, so we will do this slide and then electron tunnel ourselves to Le Chatelier's principle so we can do LCP. So let's understand qualitatively what equilibrium constant represents, what big K represents, and how we can interpret it, because it's important for us to understand the contents of a chemical reaction at equilibrium just by looking at K, the K value. So K, this number, not rate. So remember back in chapter 11, we talked about little k, rate constant. Typically, a big rate constant meant what kind of reaction? Fast or slow? Fast. Versus a small rate constant typically meant a slow reaction. So same idea here, a big equilibrium constant. You can tell by the expression that equilibrium constant is, it tends to be products over reactants. If K is a big number, you typically have a lot of products present at equilibrium, right? Because in mathematics with fractions, if you put a big number in your numerator, a big number comes out. Versus if big K is a small number, right? So like 0.001. How with fractions we get a small number is if you put a big number in the denominator, right? That's a tip that'll help you for predicting how reactions work moving forward. So if K is a small number, we have a lot of reactants present at equilibrium. And that's kind of the conclusion we can say. Where large K, more products are formed. We can also say that the forward rate constant is larger. And because we looked at this earlier, yes, equilibrium constant represents the ratio of products over reactants, but it also tells us the ratio of rate constants, of the forward to the reverse rate constant, because this idea of equilibrium is based upon the idea that the forward rate is equal to the reverse rate for an elementary reaction. So for example, here is a one-step reaction, reactants to products. We see that the forward rate is faster than the reverse rate because the activation energy for the forward direction is smaller than the reverse. So here we see, products will accumulate. K is a big number. Versus if it's the other way, if it's an endothermic reaction, reactants, products, the forward direction is slower than the reverse direction. K is actually smaller than 1, and this is because Kr is actually faster. So the rate constant for the reverse reaction is faster than the forward. Versus in the other example, the forward reaction is faster than the reverse reaction. So what I'm doing is just comparing the idea of rate constants equaling equilibrium constant and the ratio of products over reactants. But for the most part, 99% of the time, we're going to be using this relationship. If K is big, if we have a chemical reaction where it's like reactants, equilibrium, products, if K is big, there's a lot of products because K is products over reactants. Versus if K is small, you're going to have a lot of reactants present at equilibrium. And that's going to help us a lot in these coming conceptual ideas with equilibrium. We were supposed to do a demo, but they don't have the demo. Should I just text Linda? Linda. Did I do it? Okay, hold on. Okay, so we're going to skip to slide 18. Slide 18, and then let me send this text. Okay, slide 18. We're going to talk about Le Chatelier's principle. So what we're going to do is disrupt chemical equilibrium. All right, come on. And utilize the idea that, yes, I did order it. Demo. Okay, all right. We're going to talk about Le Chatelier's principle. So we're going to start with reactions at equilibrium and then disrupt them and predict what happens. So the idea here is that when we're at chemical equilibrium, okay, the forward rate equals the reverse rate. So remember I showed you talked about the analogy. It's like, okay, I have like an escalator going down, but then I'm walking up, right? Okay, and so there's a certain point where if my rate of going up matches the rate of the elevator going down, if you're looking at me from far away, I don't move because our rates cancel each other out. That is the idea of equilibrium. So what we're going to predict here is, well, what if we disrupt that equilibrium for a moment? How do we reestablish equilibrium? So here's another analogy. Pretend that I walk on treadmills, okay? And so I'm walking on a treadmill where my forward rate equals the rate of the treadmill going, like, turning, okay? How is one way you can make me fly off the back of that treadmill? Okay, so right now I'm walking on the treadmill, okay? I'm going at a constant rate so I don't look like I'm moving in space, but how could you force me to fly off the back of that treadmill? What's one way? Increase the speed of the treadmill. Yeah, if you just hit the speed button of the treadmill and make it go really, really fast, but I stay the same speed, won't I go flying off? Is there another way that I can go flying off? If I slow down, right? If it starts going too fast and I slow down, I also go flying off. So there's two different methods we can use to disrupt equilibrium, and that's what we're going to be looking at here. So other analogies, seesaw, okay, we're at equilibrium, we tilt it, how do we get back to equilibrium with that seesaw? Okay, so K, equilibrium constant, represents the concentration ratios at equilibrium. But when we're not at equilibrium, we can calculate what's called Q, the reaction quotient. The reaction quotient is calculated exactly like K. It's products over reactants. It's just we're not at equilibrium. But what's helpful to us is if we compare Q to K, the values, we can compare, okay, which way does my reaction have to go to achieve equilibrium? So reaction quotient Q, see how it's literally the same equations, products over reactants, but Q is not at equilibrium, while K, whatever value this is at equilibrium. So what's really useful to us is if we compare those values. If Q is less than K, I like to think I don't have enough products, so the reaction must move forward to establish equilibrium. Versus if K is bigger than, if Q is bigger than K, I have too much products, so the reaction goes in the reverse. So all these ideas stem from the idea that products over reactants is K, and how we ultimately calculate Q, and we can compare their magnitudes to figure out which way a reaction has to go. So we'll explore Q in the next slides, but again, what Q can tell us is, okay, we're at non-equilibrium conditions. We disrupted our reaction. How does it get back to those equilibrium conditions? So we can either talk about how do the forward and reverse rates change at that moment, How does the reaction reestablish K? By adjusting itself, and then general patterns. That's Le Chatelier's principle. The ways we will disrupt a equilibrium, these are the ways we will do it, are adding, removing concentrations, changing pressures, and changing temperatures. I'm going to teach you how to do things two ways. The quick and dirty way, that will just get you the right answer. And then the second way is the real way, all right? So I'll teach you both of how to utilize Le Chatelier's principle. The first one, quick and dirty, you just get the answer. But the second one uses the underlying concepts that matches what we see qualitatively. Okay, so for this reaction, all right, I got a couple vessels, and I want you to tell me whether these reactions are at equilibrium and or which way they have to move to achieve equilibrium. All right, so a couple ideas here. I tell you that the K, the equilibrium constant for this reaction is 1.5, so it might benefit us to get what that equilibrium expression is. It's products over reactants. So the expression that represents 1.5 is the concentration of AB squared, because there's that 2 coefficient there, times A concentration times your B concentration. Whoops. And so at equilibrium, these concentrations will multiply to 1.5, always, at equilibrium, always. So let's use this information and determine what are these different pictures at. So I've done the counting for you, or I've done the counting for you. It's just up to us to calculate what is Q at these conditions. The reason I'm saying Q is because I don't know if these reactions are at equilibrium or not. So to calculate Q, I'm just going to plug in these actual concentrations into the K expression. But again, I don't actually know if we're at equilibrium or not, so that's why I call it Q, but essentially it's K. So remember, Q or K is equal to A B concentration squared over A concentration times B concentration. So essentially, I'm just plugging in these numbers, and I'm calculating, given the concentrations of what's present, what is the ratio of products to reactants at this indicated condition. So there's 6 ABs and 1 of the other things. So what is this equal to? 6 squared, so 36 over 1. Okay, that one's 36 over 1. What about this middle one? So we're going to do AB squared, so 3 squared over 3 times 2. So what is that? 9 over 3 times 2. What is that? 6? Is it 6? No. Okay, let me do my calculation. 3 squared. Come on, y'all. 3 squared. Oh my gosh. Divided by 6, 1.5. Great, 1.5. Okay, let me highlight these. These are our Qs. These are the ratio of products over reactants at this given moment. And then the last one is 2 squared over 3 times 3. So what is that? 4 over 9. So that's basically a half. Right, those are my 3 Qs. Is one of these pictures already at equilibrium? Yes, which one? The middle one. So will the middle one change at all? No, that middle one, it's going to maintain that 3 to 3 to 2 ratio all the time, all right? So this middle one is already at equilibrium already, and the reason is because Q equals K. Okay, I told you that for this reaction, K is 1.5, so I had to tell you that, all right? Okay, so what must happen to these guys? So remember, K, Q, whatever, it's the relative amount of products over reactants. So in this first, the left one, all right, Q is 36. That is much greater than K. Okay, K is 1.5, all right? 36 is much bigger than 1.5. So I like to ask myself, I have too much what side of the reaction? I have too much products, yes, because the numerator is a big number. All right, so that means if I have too much products, which way does my reaction have to go? Reverse, yeah, in order to consume some of that product, make more reactant, and that's how I decrease Q so it becomes K. So in this reaction, this reaction shifts to the reactant side to consume some of that product, make more reactant, so Q goes back down to K. Remember, if you just remember K, Q, whatever, is products over reactants, the relative amounts, you'll be fine. So versus the third picture here, you see that Q is much smaller than K. All right, Q is 0.5-ish, K is 1.5. So you can think about this a couple ways. You can either think, oh, I don't have enough reactant because Q is very small, or you can think I have too much reactant in the current Q conditions. So which way does that reaction have to go, the third one? It has to go forward. Yeah, it has to go forward because I don't have enough product. So this one moves forward, given those conditions. So Q is really powerful. It lets us predict which way the reaction has to go to achieve equilibrium. Okay, so that's just kind of the power of Q and what it can tell us at a given situation. So let's talk about Le Chatelier's principle. There's 3 ways we can disrupt an equilibrium. I'm sorry our demo's not here, if not, definitely Thursday. So the idea is if we have a reaction at equilibrium, you can think I'm walking on the treadmill and I'm just like driving, I'm going forward, the treadmill's going backwards, and I'm just maintaining that speed. You can come over to me and screw it up. You can just screw with me to mess up my nice equilibrium, my nice workout that I've been doing. And so for reactions, there are 3 ways we can disrupt an equilibrium. We can either change concentrations of stuff, we can change pressure by changing volumes of gases, or we can change temperature. Those are the 3 ways we can screw up an equilibrium, and their equilibrium has to readjust itself to accommodate how you screwed it up. So the main idea, the quick and dirty way to do any one of these predictions of which way a reaction has to shift is whatever you do to the reaction has to do the opposite to undo what you just did, right? So if you think about like a seesaw, if you press down on like this side of the seesaw and it goes like this, to get back to equilibrium, you got to do the opposite. You got to push down on the opposite side to make it go back to equilibrium. And that's the basic idea. So, for example, if we add N2 to this reaction, so right now it's at equilibrium, we add a reactant, which way will the reaction have to shift to accommodate that addition of a reactant? It's going to shift to the products. You added nitrogen, so the reaction's going to move forward because you, one, added a reactant, and so you want to consume that reactant to make more product. So you want to undo what you just did. Or what if we remove ammonia? You remove a product. Okay, how will the reaction have to react to undo what you just did? You removed a product, so the reaction is going to shift forward in order to reaccommodate all of that product that you just lost. So both of these examples are examples of the reaction shifts forward, but for different reasons. All right, and actually the reason is because we disrupted rate law at that moment. But the idea is that add nitrogen gas, the reaction shifts forward. If you add ammonia gas, it also goes forward because you removed a product and you want to fill up that void again. Okay, so that's the quick and dirty way, where you just do the opposite of what you did, the disruption, whatever that was, you just do the opposite to undo it. But this is what's actually happening when you disrupt an equilibrium. What you actually do is disrupt the rate laws, right? Because remember that a rate law has to do with the reactants and products and those coefficients for elementary reactions. All right, so let's remember that this chemical equilibrium, it's a fast step in our mechanism. All right, there is a forward rate and a reverse rate based upon the concentrations of products and reactants. So here, that's where Kc comes from, and we know that Kc is also equal to the forward rate constant, reverse rate constant. All right, okay, so before we even talk about rate laws, just tell me, if I add hydrogen to this reaction, which way will my reaction go? Forward or reverse? Remember, you got to undo what you just did. So if you add reactant, You want to consume that reactant and move forward to make more products. So our reaction moves to the right. But why does it move to the right? The quick and dirty way doesn't do anything about concepts. The reason that the reaction moves to the right the moment we add hydrogen is because we disrupt the rate laws. When we're at equilibrium, this is true. At equilibrium, the forward rate equals the reverse rate constant. Or sorry, the forward rate equals the reverse rate. So what are we doing to this equilibrium? How are we disrupting it? We're increasing the concentration of hydrogen at that moment. That's the only thing we're changing. So whatever number was in here, right there in that part of the rate law, goes up. Whatever number that is, it's now bigger. So what happens to the forward rate the moment we add hydrogen? The forward rate, the rate in the forward direction, actually gets larger. It's faster than the reverse rate. And the reason is because we increased the concentration of hydrogen at that moment, right? So the forward rate increased its value. And so at that moment, the forward rate is now greater than the reverse rate. So we see an overall shift to the product side because the forward rate is now faster because we disrupted that rate law. But looking more into the details here, really, why? What specifically changed? The forward rate increases because the forward rate is equal to Kf times N2 concentration times H2 concentration cubed. And we saw, okay, yeah, the H2 concentration increased. But the moment we add hydrogen gas, how does the reverse rate change? Does anything change about, yeah, why are we shaking our head? Why doesn't the reverse rate change at all? There's no hydrogen in it. Yeah, that's exactly right. So we see that the forward rate increases, but the reverse rate stays the same. But because both of those things happen together and the forward rate increases, we're going to see an overall shift to the product side, even though the reverse rate didn't change at all. Because what's a common misconception that students think is they think, oh, if the reaction shifts to the product side, the reverse rate has to slow down. It doesn't. There are two ways you can go flying off the end of a treadmill. You can either speed up the treadmill or you can slow down the person walking on it. There's two ways. You can achieve the same observation. In that case, it's here, forward rate is increasing, reverse rate is staying the same. Let me do one more. Okay, let's do one more. So let me just delete all this, and instead of adding hydrogen, what if we remove NH3? What should our peepers observe? What should we observe? If we remove ammonia, the reaction shifts to the product side. So we should see the same thing, right? It shifts to the product side again. But why does it shift to the product side? Does it shift to the product side because the forward rate increases? No. Why does it shift to the, but doesn't increasing the forward rate shift to the products? It does, but not because of decreasing ammonia. Decreasing ammonia will only affect which rate law? The reverse one. And it's because this one decreases, this one stays the same, that we see an overall shift to the product side. And it's because we're disrupting the rate law. The only value that changes here is that ammonia value. And I get very passionate about this because it all has to do with rate laws, and it unfortunately came back. But the cool thing is that Le Chatelier's principle also predicts the exact same thing. Right? But here, the real way, there's more detail there. Okay, so, all right. Okay, so that was concentration. Let's do pressure. Okay, so gases are neat, where gases, they take up space, they have pressure, and in the course of a chemical reaction is that the number of particles of gas can change in your equilibrium, depending on where you are in this chemical equilibrium. So I told you, you learn the quick and dirty way first, then the real way. So for gas equilibria are very sensitive to volume changes. Because typically, when we compress on something, when we squeeze on a gas sample, typically what happens to the pressure inside? It increases, yes. Versus if we expand the volume, the pressure decreases. All right, and so when we're working with gases, that change in volume is very important. All right, so here's the quick and dirty way. The equilibrium relieves itself by moving towards the side with more or less moles of gas, depending on what you do to the reaction. So here's a generic reaction. In this reaction, you start with 1 mole of gas on the reactant side, 2 moles of gas on the product side, okay? So if you squeeze on this container, all right, you squeeze on the container, you increase the pressure inside that container, the equilibrium will want to relieve itself by moving to the side of the reaction with less moles of gas. So if I squeeze on this reaction, which way does it go? Does it go to products or reactants? Reactants, yes, goes this way. You compress on the container, it goes to reactants because there's only 1 mole of gas on the reactant side. Versus if you expand on the container, okay, less pressure, your reaction's going to make up that void of the void of gas that you don't have anymore, and it's going to move in the forward direction, right? So you expand on it, lessen the pressure, the reaction makes up for that loss of pressure by making more moles of gas. Here's my analogy, all right? So I am a plant hoarder. I like having a lot of plants. Okay, so at my house I have a lot of plants. What if I had to move into a new house and that house was smaller? What would I have to do to my plants? I would have to get rid of plants, right? I would have to move to the side of the reaction with less plants because my volume of my home decreased. Versus what if I moved into a bigger house? I can get more plants, yes. So I can buy more plants. I can move to the side of the reaction with more plants. All right, and so that's the analogy here. You squeeze on the container, you're going to move, you're going to get less plants. If I move into a bigger house, I'm going to go get more plants. All right, and so it depends on how the reaction is set up. Here it goes from 1 to 2, but it could be 2 to 1. It moves to the side with whichever has more or less. That's the quick and dirty way. Okay, now let's learn the real way. All right. Okay, so let's look at this chemical equilibrium again. A goes to 2B. So remember, this chemical equilibrium also has a rate law. Forward rate equals reverse rate. So let's just think of this. All right. Let's say at equilibrium, the pressure of A is 1 atmosphere and the pressure of B is 2 atmospheres for funsies, okay? So what happens if I have the volume of my container? What happens to the pressure of A? It increases, but by how much? To 2 atmospheres. So if I have the volume of my container, the pressure of my gas doubles, all right? So volume of container halves. Partial pressure of A will double its pressure. How will the partial pressure of D change? Or sorry, B. Also double, yes, because again, my pressure halves, or sorry, my volume halves, okay? So we doubled A, we doubled B. So at this moment, we are actually changing the pressure of both the forward and reverse rate laws. So tell me, so Kf is a constant, it doesn't change. A concentration or pressure is doubling, but B concentration is also doubling, but it's squared. So what happens the moment I have the volume of my container? A pressure increases by double, B concentration increases by double, but because B has a square in its rate law, what we actually see is that there is a doubling effect of the forward rate law, but there is a quadrupling effect of the reverse rate law. Do you see that? Because it's 2 squared. It's 2 squared. Thank you. No, it's okay. And yeah, so we see, at this moment when we have the volume of this container, that the reverse rate law increases dramatically because of that squaring effect, right, in that rate law, right? And we see that that is absolutely consistent with our plant analogy. You squeeze on your container, you move in the direction with less moles of gas, and that happens to be in the reactant side. So that's why we see the reverse direction increase its rate dramatically. And so we see the same thing when we expand on our container. If I go from having a 1 liter container to a 2 liter container, pressure of A halves. Pressure of B will also halve. So if both the pressure of A and B halve, our rate laws change at that moment. And so we see that the forward rate halves, but the reverse rate halves squared. So we see a, like divided by 4, if I don't want to do 4, let's do times a half. I don't like division, times a half. So we see they both have, that the reverse rate halves because A is first order, but the reverse rate actually goes down by a fourth because it's second order in terms of B. All right, so here we see, okay, both of them decrease, but the reverse rate decreases more. So that is why an overall forward shift to the product side is seen here. And it has to, again, do with disrupting of the rate laws at this moment. Okay, good. All right, so perfect timing, because now we'll do the last one. The last quick and dirty way, but then you'll learn the real way, is, let me just do this one. I don't want that real quick. Let's just leave you. Heat, okay, all right. So let's treat heat as a disruption we can make to our chemical equilibrium, all right? So here's the quick and dirty way. Just treat heat as a product or reactant and predict it just the same as concentration. Okay, so in an exothermic reaction, you hold a exothermic reaction, and what does it feel like? Hot, feels hot. Feels hot, exothermic, right? Combustion reactions, they hot, right? Yes. Okay, so they're hot. So that means heat is a what in terms of the reaction? A reactant or product? It is a product. So for an exothermic reaction, heat, I'm just going to call it triangle, is a product. Versus endothermic reactions. Endothermic reactions, you hold them, and what do they feel like? Cold. Yeah, so when you did, dissolution processes and the water got cold, those were endothermic dissolution processes. So triangle is a what in an endothermic? It's a reactant or product. It is a reactant. So simply, if I heat a reaction, you add triangle. And you think about it in terms of the appropriate side depending on what kind of reaction it is. For exothermic reactions, triangle is a product. If you cool down a reaction, instead of adding triangle, you're removing triangle. You're removing that concentration, and that's how we can predict which way a reaction shifts based upon temperature. So let's use this, the quick and dirty way, just treat heat as a product or reactant. So here, the dissolution of calcium hydroxide is exothermic. So triangle is a what? Product. Perfect. So what happens? Which way does the reaction shift when this reaction is heated? Okay, if we're adding heat, we're heating it, we're adding triangle. So you can just think, oh, we're adding a product. So adding a product shifts the reaction in which direction, just like we did for concentration. It shifts it in reverse. Yeah, so this reaction goes this way. It goes in reverse. Okay, because we're heating it, we're adding a product. Reaction always does the opposite of what you just did. All right, so if we heat this reaction, what should we see? We should see more solid come out. That's weird. That's usually not what happens when we dissolve stuff, but calcium hydroxide's an exception. Okay, what if we cool this reaction? So instead of heating it and adding triangle, yeah, we're just removing triangle. We're taking away a product, so the reaction's going to shift in the other direction. So when do you think this reaction, when is calcium hydroxide the most soluble? At high temperature or low temperature, just based upon what we just said? Low temperature, yeah, that's weird. Yeah, calcium hydroxide is a weird one, all right? Because usually we think, oh, to dissolve stuff, we heat it up. But calcium hydroxide is a weird one, and it actually has to do with entropy. Okay, all right, so let's do another one, an endothermic process. So here is potassium chloride. So endothermic means triangle is a reactant. So here, what's going to happen when we heat the reaction? It's going to move towards the products because you add triangle. You cool it, you're removing a reactant, it's going to go in reverse. All right? It's all about where you place triangles. So what can we say about the solubility of potassium chloride? It is more soluble at what temperatures? High temperatures. And that's typical for what salts we think of, like sugar. If you wanted to make a really sugary syrup and you want to dissolve all those crystals, typically what you do is heat up the water that you're using to dissolve it to get more of it to dissolve. So that kind of matches our intuition. Okay, so that is the true, that's the quick and dirty way to predict how equilibrium shifts with temperature. So let's do it a little bit differently here, okay? The effect of temperature and equilibrium. Here, I'm giving it to you backwards. I'm showing you the observations, and I want you to tell me, is this reaction endo or exothermic? So here are the observations. I have an equilibrium here. Iron 3+ is yellow. Iron thiocyanate is a blood red. It's a violent blood red. Also think about, what does blood, like human blood, is made out of hemoglobin? What's in the center of a heme? Do you know? Have you ever tasted your own blood by accident? Yes, it's iron, yes. And look at this complex. It's iron thiocyanate. It looks blood red because there's iron in it. So we can see some similarities in, properties and structure and composition that we see here. Okay, anyway. So the thiocyanate is blood red, iron 3+ is yellow. So based on these observations, you stick the compound in a hot water bath, it turns yellow, but it is red in a cold water bath. Is this reaction endo or exothermic? You might be sitting there being like, how the hell am I supposed to know that? Here's the thing, you just guess and check. Put triangle somewhere, heat it up, and see if it matches your observation. So I'm just going to place it somewhere. I'm going to place it right here. Okay, so I'm going to make triangle a reactant. Heat that up. What color should it turn? Based upon where I put triangle. It should turn red, right? It should move to the product side and it turns red. Is that what we see in our observations? It is not. So did I choose the right place to place triangle? I did not, so you just try again. Okay, so it's just guess and check. So I'm gonna put triangle on the other side now, and then now I'll check our observations again. Heat it. Which way does the reaction go? Reactants, it turns yellow. Is that what our observations say? Yes. If we cool it down, we consume triangle, the reaction goes in the reverse direction. It goes towards products, and it turns which color? Red. And is that what our observations say? Yes, it is. Perfect. Okay, so let's do another demo. Oh, yeah. They're perfect. I was going to write it, but I had it there. It's like I know what I'm doing. Okay, so here's the demo. We're going to do the exact same thing where we have a demonstration of a gas. It's in a tube. Stuck in a tube here, where this chemical equilibrium is between N2O4 gas, which is colorless, and NO2 gas. So this is like one of the NOx gas that comes out of your car if you don't have a catalytic converter. And this is what makes nitric acid in your lungs. This is what it looks like, is brown. So right now, based upon the color of these tubes, which side of the reaction is most dominant, the reactants or product side? Since these are pretty brown, do you agree that it like matches my coat? It's brown, so mostly NO2 is present because it's the brown. So see how I have the letters are brown? It means it's brown. So what I'm going to do is put these two containers in hot water. So this is hot water, and then we're going to put it in cold water and see how the color changes. And what I want you to do is tell me, is this an endo or exothermic equilibrium based upon the observations that we see? So it's already happening. So in cold water, how is the color of this tube changing? Is it changing that much in cold water? Yeah, the color is going what, up or down? It's down. So as we put it in cold water, which way is the reaction shifting in cold water? Yeah, back to N2O4, to reactants, versus in hot water, the color is getting darker. It's getting a lot darker, so that means we're shifting to the product side. So based upon these observations, hot water, cold water. Yeah, where does triangle go? Where's triangle gonna go? Just guess and check. I don't know, I'm gonna put it there. Put triangle there, heat it up, it should turn brown. Is that what I see? Yes, it is. So it looks like triangle goes on the reactant side. So what kind of reaction is this? Endothermic, as written, right? Versus, let's just say you didn't know, let's just say you put triangle in the wrong place. Okay, you put triangle there, and you predict, okay, you heat this up, it should turn colorless. That's not what we see. We see, oh no, it turns colorless in the cold water, so you gotta try again and pick again, right? So yes, triangle goes on the product side, or sorry, reactant side, so this is an endothermic reaction. So delta H has what sign? Positive or negative? Positive, yes, endothermic. Okay, right, so these are very expensive tubes. They don't make them anymore. Yeah, probably because they're filled with noxious fumes and they're very easy to break. Okay, so there we go, there's the demo. Chemical equilibria, how temperature affects chemical equilibria. But is this actually how chemical equilibria with temperature works? Is triangle actually a product or reactant? It is not. Okay, so this was the quick and dirty way to just predict the right answer. But here is the real reason why equilibria shifts when we change temperatures. This is the real reason. It's because when we heat up a reaction, the forward rate constant increases, the reverse rate constant increases, but they don't increase equally. What did we say about Jeff Bezos? Reactions that already go slow, do they increase more or less with added temperature? More. If you're already going slow, you increase more than if you're already going fast. So the idea here is in a reversible equilibrium reaction, the forward rate is not quite equal to the reverse rate, but one of them is already going faster. So if you heat this reaction up, both of them increase. Okay, both of the rate constants increase, but one of them increases more. And it's usually whichever one's already slower. So here's the idea, right? Rate constant is not just products over reactants, but it's the ratio of the forward rate constant over the reverse rate constant. Remember what we said about rate constant? Rate constant increases when either temperature increases, hot reactions go fast, or when the activation energy is small. Small activation energy, fast reaction. So we know as we heat up reaction, rate constant always increases, but a reaction with a large activation energy, basically already going slow, takes more with that change in temperature, right? If you give me $10,000 versus you give Jeff Bezos $10,000, it's gonna make a bigger impact on my life, right? Because I'm already going slow, right? Versus, both of these reactions, they get faster, but one of them increases more. So let's think about this. Here is what is this? An endothermic reaction. So we have reactants goes to products. So for an endothermic reaction, triangle is on what side? The reactants or product side? Reactants. So you heat this up. What does Le Chatelier's principle say happens? It moves to what side? To the product side. Yeah, that we heat it up, we add a reactant, it pushes to the product side. So Le Chatelier's principle predicts, we move forward, that K increases because we make more products. Equilibrium constant increases. So let's work our way through this reaction. So right now, for an endothermic reaction, the reverse rate constant, I'm going to make this really exaggerated. The reverse rate constant is really big. It's really big. It's really fast already because it has a small activation energy versus the forward rate constant is really small because it has a large activation energy. Do you see that? The forward rate slower than the reverse rate? Okay, heat this reaction up. What happens to the forward rate? When you heat stuff up, they always get faster. What happens to the reverse rate constant when you heat it up? It goes faster, but which one gets faster more? The forward or the reverse rate? Which one gets faster more? Which one gets more use out of that increase in temperature? The one that's already going slow. So the forward reaction actually increases more because it's already going slow. Okay, both of them increase, but the forward reaction increases more. So what does that mean? How does the value of Kc change? Remember, Kc is equal to Kf over Kr. So Kf increases, Kr increases, but Kf increases more. So how does the value of K change? It gets bigger, right? If Kc gets bigger, how does the ratio of products to reactants change? What should you have more of at equilibrium if K is bigger? You should have more products, right? If K is a big number, it's products over reactants. Okay, so if Kc is a big number, you're going to generate more products. Is that consistent with Le Chatelier's principle? You heat it up, it moves to the product side. Yes, they are absolutely consistent. So here, what we're learning is that equilibrium constant is sensitive to temperature, not because triangle is a product or reactant, but actually it's because the value of the equilibrium constant is changing, because the values of the rate constants are changing unequally. And so in this case, it's a endothermic reaction. It shifts to the product side. K is getting bigger. So let's do it the same way, but for an exothermic reaction. So it's the exact same thing, but this time in an exothermic reaction, reactants to products, triangle is a product. So if you heat up an exothermic reaction, what is predicted to happen to the equilibrium? You should make more what? Reactants. So the value of K, the equilibrium constant, should change how? Should it get bigger or smaller? It should get smaller, and that's exactly what happens. So the Kc value should get smaller because we make more reactants. So let's think about this. All right, you are walking up and down this hill. Which hill is it faster to go around? The forward direction or the reverse direction? The forward is a lot faster to get over. So here, this is Kf, the forward direction. Really, I'm exaggerating it a lot. But the reverse reaction is really slow. Still happens, but it's slow. So when we heat up the reaction, the forward rate constant increases. When we heat up the reaction, the reverse rate constant increases. But which one increases more? The forward or the reverse? Which one is already going slow? The reverse. So that one is going to get more out of that increase in energy. So the reverse reaction increases more, right? So what we see is that, remember, Kc is equal to Kf over Kr. Kf increases, but Kr increases a lot more. So how does the value of K change the moment we heat this exothermic reaction up? It gets smaller. Okay, Kc gets smaller because now we have a bigger number in the denominator. So Kc getting smaller, is that consistent with what Le Chatelier's principle says? You heat the reaction up, you make more products. It absolutely is. And it's because the value of K is changing because the rate constants themselves are changing, but changing unequally, right? This is one of my favorite parts of the chapter just because it's like a conceptual thing and then I unveil the curtain and you sound a lot smarter, but it still matches everything that we learn about conceptually, about Le Chatelier's principle. So you will explore this in the LCP lab starting tomorrow, some of you, the different ways to affect chemical equilibrium. We can either add or remove reactants or products. We can change pressure, though I don't think you're going to do that in lab, or you can change temperature. Okay, so let's just review everything and then jump back to slide 8 or whatever. Okay, so let's review. Remember, whatever you do to the reaction, the equilibrium does the opposite to undo what you just did. So which way does the equilibrium shift if we do the following things? So I tell you, here is an exothermic reaction. There's a hint. If I tell you it's exothermic, I'm actually telling you where triangle goes. So where should triangle go? It should go as a product because it's exothermic. Exothermic reactions feel hot to us. Okay, that'll be useful if we have to change temperature. All right, so which way does the reaction shift if we add N2? N2 is a reactant, so this reaction is going to shift forward. Add a reactant, move to products. What if we decrease the amount of hydrogen? So now we're removing a reactant. So which way is it going to move? Backwards, yes, to undo what you just did. So I removed a reactant, so I'm going to undo that by moving backwards to put back, to replace that reactant that you just took away. You know, I can say, you know, decrease amount of reactant or product, but that's kind of hard to do. So here, this one's a lot more realistic. Let's say I neutralize ammonia. Ammonia is a base. So I could say, yes, you remove ammonia. Which way does it shift? But removing ammonia sounds simple, but it's not. To remove ammonia, I actually have to react it with something so it pulls it out of the chemical equilibria. One of the ways I can do that is by reacting it with an acid. So let's say I add acid. Acid reacts with ammonia. That then in turn removes it from the chemical equation. So this is just a fancy way of me saying we are removing ammonia. Right? That's how I remove ammonia, is by adding acid or something. There's a lot of different ways we can remove components of a chemical reaction. You find something that it can react with. So really, we're saying I'm removing ammonia, so I am removing a product, so it's going to move in the forward direction. It's just a fancy way of me saying remove product by making it react with something. All right, so those were concentrations, so let's talk about pressure. Okay, so the pressure of the reaction vessel doubles by compressing the container. So I'm squeezing on the container. Which way is the reaction going to go? Towards the products or reactants? Products, because there are less moles of gas on that side. Okay, I squeeze on the volume, smaller house, less plants that I can have. So I want to move to the side with less plants. Versus on the reactant side, there's 4 moles of plants, but on the product side, there's only 2 moles of plants. So that's how I can accommodate that increase in pressure. All right, volume of the container doubles. Which way do I move? Reactants, because I can now buy more plants, 4 moles of plants instead. All right. What if we heat the reaction? Which way does it go? Reactants, yes, because triangle is a product, and then it is cooled, so we're removing triangle, so it goes to the product side. And that's how you do it. That's Le Chatelier's principle, but also the real way to do it. And you know that I'm going to test you on both. Do you know the Le Chatelier's principle? Can you just predict which way it moves? But also, why does it shift forward? Why does it shift in reverse? Oftentimes it has to do with changing the equilibrium, changing the rate laws at that specific moment in time. Okay, so we got 20 minutes, so I'm going to go back and do 3 more slides and then save ice tables for Thursday. So let's go back to slide 8 and talk about other ways that we can manipulate and understand K and work with it. So let's think about it this way. K, equilibrium constant, is products over reactants. So if I write, A equilibrium B, the K expression is B over A. But if I reverse the reaction, the value of K changes, but also the equilibrium expression changes. Because if I reverse the reaction, A is now a product, B is now a reactant. So what we see here is that if we manipulate K, like the expression of K, we also manipulate the value. If that sounds familiar, like Hess's law, it's basically like Hess's law, all right? So here's how we manipulate equilibrium constant. Here is a chemical equilibrium. Let's write the K expression for this reaction. Okay, so big K, products over reactants. So my product is C. My two reactants are A and B. Cool. So let's look at the other reaction. So how are these two reactions related to one another? They are reverses of one another. So tell me, so let's call this K, yeah, okay, KC, it doesn't matter. Let's write the K expression for the second reaction. It is A concentration times B concentration over C concentration. So what do we see here? Two reactions, if you reverse them. Instead of, delta H is what we did if we reverse a reaction, we just change the sign of delta H. But what you see here is that if you reverse a reaction, instead of multiplying by -1, we take it to the -1 exponent. All right, so they're becoming exponents essentially. So you reverse a reaction, you flip the numerator and denominator of your K expression because you're literally changing the identity of your reactant, your reactants and products. So yeah, flip a reaction, reverse it, you take the reciprocal of the K value. Very similar to Hess's law. Okay, let's look at another one. Let's look at these two reactions. What is the K expression for A goes to B? B concentration over A concentration. And then B to C is C concentration over B concentration. Cool. Now, let's take these two reactions, A to B, B to C, and let's add up these two reactions. Pretend this is a two-step mechanism. A goes to B, B goes to C. What's the overall reaction? A to C, because the B's cancel, so the overall reaction is A to C. So what is the new K expression for this guy? It is C concentration over A concentration. So how can we relate K1, K2, and K3? K1 times K2 equals K3. If you look closely, you see that the B's cancel because one's in the numerator, one's in the denominator there. But what we see is, remember in Hess's law, you added two reactions, you added their enthalpies. But what are we doing here? We add two reactions. We're not adding their K's together. We are multiplying them. That's all it is, all right? So I don't find that to be like new learning. It's just like applying something we already know, just extending it. So here are the rules, right, for manipulating K expressions. Here is the OG, the original K expression. N2O4 gives us two NO2s. You ask yourself, how is this reaction different from this reaction? We are reversing it. So what do we do to the value of K? What is the K for this new reaction? If I reverse this reaction, I take the original and take it to the -1. If I reverse a reaction. It's like Hess's law, but you take it to the exponents instead. All right, what about this reaction? This reaction, you're taking the original reaction and you're doing what? You are multiplying by 2. So if I double the reaction, we're not going to double K. We're actually going to take K of the original and we're going to square it instead. All right. All right, so here are the rules. I forgot to write this down. The general rules: if we reverse a reaction, you take the original rate constant to the -1 exponent. You double a reaction, K squared. Triple, K3, very good. Have a reaction, what do you think? K to the 1/2, yeah, K to the 1/2, which is also the same as K to the square root, root 2. All right, what if you add two reactions together? You multiply those K values together, no matter how many you're adding together, right? So you're multiplying them, right? What if I, instead of having a reaction, what if I reduce it by 1/3? What do you think? Yeah, it's K to the, you can think the 3rd root, but I don't want to spend time on the exam looking for where the cubed root button is on my calculator. So instead, recognize that a cubed root is the same as taking K to the 1/3. All right, that a cubed, so a root 4, right, is the same as taking k to the 1/4 power, right? Don't spend time looking for the cubed root on your calculator. Just take it to the 1/3. It means the same thing, right? Same thing here, that the regular square roots is to the 1/2 power, right? All right, so those are the manipulations, really related to Hess's law, and you'll be fine. So we'll stop, we'll do this slide and then stop here. So let's manipulate K expressions, right? Where these K expressions, you have your target reaction, and then you have your given reactions and Ks. So just like Hess's law, you need to ask yourself, how do I combine these reactions to get what I want, right? So in this case, look and see where do things come up. So 2 NOBRs right there, the product, and we see, oh, that shows up in the first reaction. You ask yourself, is it in the right place? Is it in the right side? Yes. Is it in the right number? Yes. So it doesn't look like we have to manipulate that first reaction at all. We can leave this one as is. But the second reaction, a little bit different. Notice that there's N2 and O on the product side, but N2 and O is on the reactant side in the target reaction. So what should I probably do to that second reaction? Flip it. Yeah, so let's flip it. But if I flip it, what do I have to do to K? Take it to the -1. Yeah. So let's just rewrite that second reaction. So you have N2 plus O2 gives you 2NO. And so if you add that to the first reaction, so there's the first reaction, there's the second reaction. If you add those two things up, you see that the NOs cancel, and you are in fact given, you're left with that target reaction. So the K for this target reaction is equal to 2. So we kept that first reaction as is, but the second reaction, we flipped it. So we have to take that second one to the -1 power. And so you do get a Kc rather small, is like 9 times 10 to the -31. Right? So we're going to stop there. On Thursday, we will talk about equilibrium constants and using ice tables. So this is quite math heavy, so I didn't want to start something halfway, and I wanted to save myself some time on the road. So remember, I'm going to just cancel office hours so everyone can get home safe. If you really need to talk to me, you can walk with me to my office. But have a good one. Stay safe.